Okay. This vector is in the YZ plane, okay, or plane parallel to the YZ plane, right? Okay, it's in the plane y equals whatever y equals here, okay? So being in the YZ plane, I can come over here and let this be the unit vector J. Okay. And this vector is a multiple of K. Now, it's not J plus K, that will put us at 45 degrees again, right? Okay. It's J plus 0.15 K because you got a rise and a run here within that constant X plane. I said Y equals X equals whatever X is here, and you got a plane parallel to the YZ plane. Within that plane, you have the J vector in this direction and the K vector in this direction. And if the slope of this thing is 0.15, the rise over the run is 0.15. And you get that by just letting this equal the whole darn J vector, and that's 0.15 K. Now, if I want a unit vector in this direction, and sometimes I do, well, I'm going to divide that by the square root of 1.0225. Okay, 1.0225. That's about 1.012. You got to divide that, so it's going to be about 0.99. Okay, J, and it's pretty close to 1.15. Okay, well, you can make that into a unit vector if you need to. It's not going to be necessary, but sometimes it's convenient to do that. Okay, in this plane, well, your x-axis is in this direction, and I think it's going to get a little clumsy when I do this, but you can have an x-axis coming out here. The z-axis going over here. You can let this be the I vector. Let this be negative 0.25 K. So now I have two vectors. Okay, so I have okay. So give me a vector, this normal to this plane, perpendicular to the plane. Okay, so normal vector is going to be the vector perpendicular to the plane. You got two vectors in the plane, they aren't parallel, so you can do the cross product, and you're going to get a vector that's perpendicular to the plane. And everybody pretty much knew that. Everybody did know that. Okay, so the normal vector is going to be it'll be this. And that's going to equal, well, I dot J is what, K, right? And I dot K is negative J. So that's going to be negative 0.15 J. And then K dot J is negative I but you got a negative on this, so you're gonna have a positive 0.25 I, and you're done, because the only thing you got left is a K times a K, right? K cross K. And then if we want to put that in the usual order, I put it down in the order that the distributive law dictates. It's this. Okay. So, and I wouldn't bother putting this into this, into the determinant. And then figuring out, what you do with the determinant and everything. Quicker just using distributive law. Now, if you got three components on each one, then the determinant's very handy, okay? You ought to be able to do it either way, so you can make a judgment, what's easier in this case. All right, of course, we do it by machinery, machinery does determinants. So, up to you. And let's see if this makes sense now, because what I did last time didn't make sense there for a while until I got all my slides straight. Okay. We're talking about a reasonable estimate on this block. Well, here's our point XY down in the plane, and up here's our point XY, F of XY. So right there's our slope in the X direction. We said, okay, this thing's actually vertical. Then the slope is maybe about 0.15. And then here, well, let's just turn it around so we can see. The X direction's that way. And it's a little steeper. At least I assumed it was a little steeper. So we said maybe the slope's 0.25. But of course it's negative because there's a positive X direction in the direction my finger's pointing, right? This thing's coming down and it comes toward you. And if you're on the screen, or if you're watching the video, the x-axis is pointing right at you. Okay. And this represents what we have. And now we want the A normal vector. Okay, well, if I use it for the normal vector, I have a piece of pipe that I went and demonstrated the area of a third area of a cylinder in physics class. Carried it all the way up there. Okay, but there we got it. Okay, and we can see that it's tilted forward in the X direction, that being the X direction, and it's tilted backward in the Y direction. Y direction being that way, this thing being tilted. My thumb doesn't go back forward. That's that way. Okay. And that's exactly what this gives us. Positive slope in the I direction means it's sloped toward the screen. Negative slope in the J direction gives us this. And those slopes come right out of these vectors. Okay. So yeah, did real well with that. So now we can find the equation of the plane. If we know X and Y, right? Okay. So the equation of the plane . Take that and we got it with the vector. Okay. I'm going to call this X naught, Y naught. Okay. So whatever the coordinates of this point are. Okay. The vector from this point out to point X, Y, Z on the plane is X minus X naught I. Okay. Your point is X, Y, Z out there. You start from X naught, Y naught, Z naught, naught to X, Y, Z. Your X changes by X minus X naught. Your Y changes by Y minus Y naught. Your Z changes by Z minus Z naught. So there's a vector from X, Y, from X naught, Y naught, Z naught to an arbitrary variable point on the plane. That's what I see. And that has to equal 0. Okay, well, there's your equation. Now, of course, you probably want the equation expanded out, and you're going to get this. And you can write that as so right there's the equation of your plane. Everything on this side is just a number. If you know what x naught, y naught, and z naught are. So for our block, that's a plane of equation z equals f of x, y. Okay, or the function z equals f of x, y, the graph of z equals f of x, y. It is where it is, there's your equation. Well, let's say x equals whatever, y equals whatever. You pick a value for x, pick a value for y. You have these things anybody else, it shouldn't be. Pick a value, okay? Pick an x or y. Now z is going to be 8.2. 8.2 centimeters, that's how high it is. And then this equation will be in centimeters. So wherever you think this is relative to the origin. Think the origin's over there, up there, back there. Okay. Pick your x and y, and you determine where the origin is. Okay. And then work out the equation. Just do the numbers. Okay. Now, x naught's -1, y naught's 1, z is z naught is 8.2. And I had x, y, z here. You should have made it x naught, y naught, z naught, because that might have put a confusion. You get this equals, well, that's going to be -0.25 plus 0.15 minus 8.2. So you get 0.25x minus 0.15y plus z equals -8.3. Okay. That work? And I use these numbers in an attempt not to make a stupid mistake in my calculation. I don't think I put that. Okay, then the question is this thing above or below the z-axis? When it intersects, does it intersect the z-axis above or below the xy plane? Well, that's fairly clear that it's gonna be below, because on the z-axis, x and y are both zero, so you get z equals -8.3. So 0, 0, -8.3 is below the origin, okay? And you're below the XY plane. If you use a big enough numbers for X and Y, or actually. Yeah, you get the signs right and everything. It's easy to get numbers that make this negative. Okay, big number for Y, small number for X. And then I'd be adding a positive number to both sides. If the number is big enough, we can have this thing above the XY plane. Above the origin, okay? Intersecting the Z axis above the origin. Okay, well, so be it for that. Okay, so everybody's got an equation. Everybody's got the same thing on the left-hand side. Depending on your choice for X naught and Y naught. You know what? I messed up my calculations. Despite choosing easy numbers. It'd be a plus 0.25. So that should be 8.6. Okay. Negative 0.25. Epsilon's -1 is plus 0.25. And 0.25 is 0.4. And it's not -8.6. No, it's -7.8. Okay, get a big number for X and a small number for Y. Would raise that to a positive. And you can think geometrically about what that means. Thing is sloping down in the X direction. So if X is big, you go way out the X axis. Okay. I have a point down here, it's gonna slope back toward the origin. And you work that out. I'd have to draw it. I don't want to do it with waving my hand. And what I just said, wrong, a big negative number for X would do it. Way out there. Okay. Now we want to do another plane. And what I want is one of these that isn't flat. Look at this. Okay, so here we have a block. You can see what its edges look like. If I do a tangent line here, yeah, maybe the slope is about 0.1, a tangent line here. Maybe it's about, look at this. Slope is going to have a magnitude of about maybe 0.4. Okay, so I'm going to say slope has a magnitude of 0.1 here in the Y direction and a -0.4 here. Fair enough. Okay, well, we can do the same thing, right? So we get another plane. Yeah, let's go ahead and do that. They're a little bit more here. And that'll be God when we need it. Yeah, let's do it right. Okay. So let's say that our slopes are 0.1, so that the vectors These vectors are in the plane. So. Normal vector. Is gonna be the cross product. And I'm gonna attempt to do the cross product in my head, okay? So we get. Okay. And then I cross K. Negative J. And K cross J. Negative I. We have this, okay? Let's assume a point. I'm gonna have to measure. This thing. That's easy. I just measure Z. Let's assume the point. 5, -3/6. So the tangent plane is going to be 0.4x minus 0.1y plus Z equals, be careful, -0.25. No, it's not -0.25. I better write it out. Except I'm going to write it out this way. Okay. I think I've written that out right now. What I mean by this f sub x and f sub y. I mean, partial derivatives with respect to x and with respect to y. Just an abbreviated, easier to write notation that you're going to see plenty of. Okay. And let's see if that matches. That should be negative f x minus f1. And then this should be positive f x, positive f1. Okay. Now, that's it. It comes in right off if you do it step by step. Don't skip a bunch of steps like I just did, okay? Don't take my word for it, that's the way it works, it matches what we have over here. Because over here, our FX was negative 0.25 and our FY was plus 0.15, right? In other words, here, back up. The slope is the partial derivative of this function with respect to y. Okay, x is being held constant, y is varying. And the derivative of this function with respect to y should be 0.15. Okay, well, if we solve this for z, some of you did, we'll end up with a negative 0.25x and a plus 0.15y on the other side. So this equation could have been written. Another good place to write. I'll write a small z equals written a little bit small. You see, if we solve for z, these signs come negative, okay? And if z is your f of x, y, then your partial derivative of this with respect to x is going to be negative 0.25. With respect to y, it's going to be 0.15. So that the slopes of these things represent partial derivative with respect to x, but with respect to y, partial derivative with respect to x. Make sense? Okay, it's a fairly straightforward idea. I should have explained a little bit before that. Okay. So our tangent plane would be this, and then our fx x naught, well, x naught is 5, and fx is negative 0.1. That's going to be negative 0.5. Fy is 0.4. 0.4 times negative 0.3 is negative 1.2. So that's, I've already lost that. It's negative 0.5, negative 1.7. That would be an equation for a tangent plane. So fx would be your partial with respect to x, and that partial is clearly negative 0.4. That's 0.1. And so that's relating these partial derivatives, this function, to the picture and to the block. Okay, well, the point is now, I've got an equation for this plane, and I've got an equation for this plane. So now what I want to do is I want to find an equation for the intersection of those planes, and an equation, set of parametric equations, symmetric equations, whatever you want, for the straight line when those two planes intersect. Because when two planes intersect, they do intersect on a straight line. Okay, we can prove it. But very obvious, take two planes of glass and intersect them. Intersection is going to be a straight line. Take one plane and then bring the other plane together with it, you get a straight line. So how are we going to get the intersection of these? Okay, I don't know when I had the recording on, when I have it off. But we, what in the world? Okay, yeah. Okay, we had found an equation or tangent line, normal line to the block and the equation of a plane, assuming values of x naught, y naught, and z naught. And I believe that was all recorded. Then we got 0.25x minus 0.15y plus equals negative 7.8. And that was using these vectors and the cross product to give us the normal vector. The normal vector then being this, and then using that normal vector and the point negative 1, 1, 8.2, we got the equation of the plane. Then we went to a different block. Here, now this block doesn't have a flat surface, it's not a plane. But we estimated partial derivative with respect to x being this slope, with y being this slope, partial derivative with respect to x being the slope tangent here. It takes the cross product, we get another normal vector. And then making certain assumptions, we get a plane. So our normal vectors we estimated were this and this. Not our normal vectors, are vectors in the plane, okay, the vectors that we get at the corresponding point of the second block. So here are the vectors, cross product is this. And then we just assumed the 0.5, negative 3, 6. 6 was actually measured 6 centimeters altitude at the corner of that block. Assuming this point, we get the tangent plane. Okay, now tangent plane turns out to be negative fx minus fyy, where fx is, in this case, 0.1, fy is a negative 0.4. This notation represents partial derivative of f with respect to x, partial derivative of f with respect to y, where f of xy, z equals f of xy is the equation of the plane. Same model we used over here. So I've got a little extra notation on here. You can compare with the result we got over here. We got a 0.25x that corresponds to negative fx, x. Fx being the partial of f with respect to x at the corner point. And for this, let me take a look at the screen real quickly, make sure we can see it as barely we can. Okay. And the slope in the x direction was negative 0.25, which gave us a negative 0.25 carry. So the 0.25x here corresponds to negative fxx. Negative 0.25 is the slope at this point, and that's the partial derivative of f with respect to x at that point. Okay. Then the fy in that case was 0.15, and a negative fy, y would be a negative 0.15y. Then we have z. And then we have, okay, we're over here. We have 0.25 x naught, 0.15 y naught, and minus z naught. Okay. We have 0.25 times whatever the x naught is. That's your fx times your x naught. Okay, so it's fx x naught. And this is fy x naught. And then we have minus z naught, the same as we have here. So this matches up with this. For now, we understand these quantities, fx and fy, as being the partial derivatives. Okay. So that's equation of the tangent plane. Of the equation of tangent plane. Okay, so there it is. And all I did then was substitute the 5, negative 3, 6, and the values of fx and xy, which were 0.1 and negative 0.4. I'm sorry, negative 0.4 and 0.1. And did the arithmetic, and there's the equation of the tangent plane. Nobody had any trouble doing that. Okay, so we get this. Okay, there's the equation of our tangent plane, and we could write that as z equals f of x, y equals all this. Okay, over here, this could be, okay, well, this equation could be solved for z. So this plane would have equation z equals negative 0.25x plus 0.15y minus 7.8. So now we have equations of these two planes, and what I asked was, okay, these are two planes, they're not parallel because they have different normal vectors. So these planes are going to intersect. Where they intersect is a straight line. We want to find parametric equations of that straight line. So that was the task I set. Now all I have to do is find, yeah, board. Okay, so here's equation one plane, here's the equation of another plane. How do we find the equation of the intersection? Well, we can set z for this one equal to the z for this one. Okay. If we're on the intersection, then the z coordinates will be the same. Where are the z coordinates the same? Well, let's see. Set this expression equal to this expression. Here it is. Okay, well, we can easily put that in the form. Turns out to be 0.15x plus 0.05y equals 12.1. We just put all our x's on one side, all our y's on the other. And that's what we end up with. This is the equation of a line in the xy plane. Okay, so let's just go with the xy plane. Here's x, here's y. I didn't label it, but probably should have. Okay, here's x. Here's y. What's this line look like in the xy plane? Because we can see clearly that it's a line. Well, we find the intercepts. Let y equals 0, we get x equals pretty close to 80. Okay. Let x equals 0, we get y pretty close to 242. Very easy to solve. Okay, so here is this line. Now down here we go to 3 dimensions, x here, y here, z here, and we draw that line. And just for emphasis, draw this line. Okay, so this line in the xy plane matches this line, which matches this equation. The line of intersection lies in a plane above and below this line, and parallel to the z. So vertical plane corresponding to this line here. Okay, so we want to get parametric equations. Well, it's easy to get parametric equations. We've got enough information. So we let x equal t. Well, if x equals t in this equation, we get y equals approximately 242 minus 3t. Just plug in t for x and solve for y. You're going to get something very close to this. So here's a set of parametric equations for this line, and that would be this line. Now all we need is parametric equation for z. Well, we have, well, z equals this. Yeah, just use this, or we could have used this and we'll come out the same. Give or take round off there. Z equals this, so we have x, well, x equals t, so we plug in t. Y equals 242 minus 3t, we plug in 242 minus 3t, and we do the arithmetic. And if I did it right, we get z equals negative 0.7t plus 28. And I think that's probably about right. Okay. Whether it's right or not, that's the way it's done. And now we have equations of a straight line. Our making equation for a straight line. We could eliminate t among these 3 equations, get symmetric equations. Well, let's now think, I could ask, okay, what's a vector in this plane? Okay, what's a defining vector? I'm sorry, for this line. Okay, if this line is either above or below turns out it's above the axis here. And it's kind of like maybe it's like in this plane. Okay. So what can we tell about this line? Okay, well, let's go back to what we know about lines, because nobody's able to give me a good answer. It's been a couple of weeks since we did this. But remember that a straight line can be modeled by a point and a vector. And you have this point and a vector, and then all the points that lie on the line defined by this point on the vector are on that line. Okay, that's how we define a line in terms of point and vector. Okay, so if XYZ is on the line, then the vector from X naught, Y naught, Z naught to XYZ has to be a multiple of this vector. In other words, the vector from here to here is a multiple of this vector. Call that multiple T. You'll see that XYZ equals X naught, Y naught, Z naught plus T times your ABC. So that X equals X naught plus 18 and all that. And this should refresh your memory. It seems to with everybody in the class. Oh, yeah, I remember that. Okay, well, you used it to get answers. Did you really understand it? No, but you got to see it 2 or 3 times before you do. So this is at least the second time. And this is really should be about the 3rd time. You really should understand it at this point. This is the picture you want to see when you think about the equation of a straight line. And when you look at these equations, and you want to put all this together so you have a good understanding, a good picture, and a good picture helps you figure out how to use the information. Well, okay, so here are our parametric equations. In the case of this line, X naught, Y naught, Z naught could be any point well, okay. Just looking at what we used. Okay, we could have used this 80 here would be the point 080. That could be our X naught, Y naught. And actually that was never mind. 080 and whatever we get from 0 and 80 for our Z. Okay, to give us a point on the line. Many different points on the line, but we were given points like 5, -3, 6. I'm still trying to see what we used. Did it? I don't remember it. Okay, we used X naught, Y naught, Z naught equals 0, 2, 42, 28. And okay. The X naught, Y naught, Z naught, I used the T equals 0 point. So when T equals 0, X is 0, Y is 242, and Z is 28. So here's our point. We could use this point with this normal vector, these parametric equations, we get the equation of the line. Okay, so that's pretty straightforward. But here are our 3 parametric equations. And the thing we're looking for is a vector in the direction of the line. That's what I ultimately asked for. And we can then see if these are parametric equations, our A, B, and C are the things that are multiplied by T, which is 1, -0.7, 242, 1. I'm sorry, 1, -3, 242. And I put a point in front of that 3 shouldn't have been, but the 0.7 should have been there. And it looks like I wrote down some of that stuff wrong. B1 for the I, -3 for the J, and -0.7. All right, anyhow, there's a vector along the direction of this line. On any point on the line, use this vector. You got a definition of the line. Switching gear. You have some questions in homework about the total differential. Total differential is df equals fx dx plus fy dy. Okay. What does fx mean? It's partial derivative with respect to x. It corresponds to the slope of this side. Okay, the slope, which might have estimated as 0.15 or whatever. Okay. And if you take the equation of that function for the straight line, I'm sorry, the tangent plane that we got using this slope and this slope. If you take the x derivative of that, you do get this slope. Okay, so fx is this slope. You multiply that by dx, some tiny increment of x. And the slope is the rise over the run in this direction. Okay, so if you multiply the slope by the change in x or the change in y, you're going to get the change in z due to the way x behaves. Okay, so if we want to go just from this point to this point, if this is the x direction, we've got it. If I can do just a little more here than I was able to do in class. So let's say we want to go to this point. Okay, so we want to do the derivative as we go in this direction. Okay, I've got a couple of projection lines here. I'm trying to, my screen isn't showing me a very good picture of what I'm doing. Let me try again. It's also jumping around all over the place. Okay, we're going to go from here to here. We can follow this slope up to here. And then since the top is flat, we can follow this slope up to this point. Okay. We have our, let's say this is our delta x or dx. I can't write on this, but it's too broad. But we've got like a dx here and a dy here. If we multiply our dx by our slope in the x direction, we get the rise in the x direction. We multiply our slope in the y direction by our interval in the y direction. We get the change in f due to y. So this is a change. What I'm saying is this expression represents the rate of change of f in the x direction multiplied by the change in x. Rate of change times the change in x gives you the change in y, or in z in this case. And I say it's a change in f. Okay, the change in the value of the function f due to the increment dx at whatever point you're working on it. Okay, and this is the same thing in y. So rate of change with respect to y times the change in y gives you the change in f due to the change in y. So the change in x here, say this is a change in x. Okay, combine that with the slope in the x direction, it gives you a change in the value of f. This is a change in y. Multiply that by the slope in the y direction. It gives you how much this thing rises and falls due to that change in y. You add the two and you get the total change in f as you go from this point to that point. So there it is, called the total differential. And then I did a quick approximation. We're going to approximate the square root of 5 using the differential. This is just one variable. You want to review this in one variable from the calculus 1. Make sure you understand it there and understand the geometry of it. Okay. In this case, f of x is the square root of x. And we just use f prime of x. We don't have to use an f sub x and x sub y because there's only one dimension. So we just use f prime. And there it is, 1 over 2 square root of x. Near x equals 4, df change in f is approximately equal to fx, which is I wrote f(x), I should have written f5. F prime times the change in x. F prime is the rate at which x changes. Multiply it by the change in x, you get the change in y. Okay, f prime near x equals 4 is equal to 1 over 2 square root of 4. Well, that's 1 over 2 times 2, 1 over 4. Slope is 1/4. We multiply that by a change in x, and we get, well, 0.25 times a change in x. With the decimal form. If dx equals 1, and why would we want dx to equal 1? Well, we want to see what this is equal to near at x equals 5. Okay, so from x equals 4 to x equals 5 in this function, we have a difference of dx equals 1. Now, that's not a tiny increment, so it's not going to be a totally accurate approximation, but we're going to use it anyway. If dx equals 1, then df is 0.25 times 1. The change in f is the rate of change, which is the derivative at the when x equals 4, multiplied by the interval from x equals 4 to x equals 5, which is 1. That means the change in f ought to be pretty close to 0.25. Now, this is a square root function. The graph looks like this. Okay, by the time you get out to x equals 2, it's not got all that much curvature. So maybe we get a good approximation. Well, our approximation then to the square root of 5 would be, well, when x equals 4, f of x equals 2. And so it's going to be 2 plus whatever change we get by moving one more unit, which is approximately then 0.25, which is this differential term. Okay, that gives us 2.25. Well, 2.25 squared, 2.2 squared is 4.84, 2.3 squared is 5.29. 2 is a little closer to 4.84 than it is to 5.29. Meaning that the square root is going to be a little closer to 2.2 than it is to 2.3. So 2.25 just kind of splits the difference. The actual derivative, the actual function, I think the square root is between 2.3 and 2.4. Probably close to 2.3, maybe closer to 2. The derivative is between 2.2 and 2.3. Sorry, it's getting late. A little closer to 2.2 and 2.3 because of the 4.84 and the 5.29. You think about that. So this is a little much, but it's no less than 2.3. Square root of 5 is no less than 2.3. So it's a pretty good approximation. If I put this in the picture, here's your square root function. And let's say here's where x equals 4, y equals 2. The slope of the tangent line is 0.25. If I move over to x equals 5 and follow the tangent line, my run is 1. My rise is slope times the run, which is 0.25. So this tells me at this point ought to have value 2.25. This is the square root curve. Now the curve has some concavity. It actually goes a little bit below the tangent line. So here goes your curve, and it actually comes in a little below the tangent line at 2.36 maybe. Um, 2.26, 2.23. 2.236, okay, between 2.23 and 2.24. So that's where this is going to be. The tangent line is straight. This thing's curving downwards. So the tangent line is a little above the actual function. Tangent line tells us that we ought to be at 2.25. The curvature tells us we're going to be a little bit below that. Okay. So that's kind of a picture of the differential, something you should have mastered in calculus if you mastered the something, and didn't forget it all. We extend that here, instead of just one contribution to the change in the value of the function, we have one due to the slope in the x direction, one due to the slope in the y direction. I recommend that you understand differentials at that level, because you're going to need to understand a lot of stuff that's kind of based on the idea of the differential as we go through the next few sections and get into directional derivatives and gradients and all kinds of other stuff, and even chain roots. Okay.